I'd now like to introduce you to Bruce Martin, who is going to come and talk about the Stavros Nicholson Foundation Cultural Centre. Bruce is an Associate Director at Expedition Engineering, and he's been leading the team on this project, and they believe that it's the largest canopy in a ferrisment in the world. Bruce.
Thank you.
Something to live up to.
So it's a bit daunting coming after Michael and Paul. I'm very much a new kid on the block. And as Jay said, I'm going to talk about the ferrisment canopy over the Stavros Nicholson Foundation Cultural Centre. The canopy is 100 metres by 100 metres, and that's 1.5 Premiership football pitches or so. And it's there to support photovoltaics, which will provide the day-to-day running energy for the centre. The cultural centre is it's three things really. There's a new home for the Greek National Opera, there's a new home for the Greek National Library, and there's a reasonably large urban park. And the cultural centre is a gift from the Stavros Nicholson Foundation to the Greek state. So the foundation are paying for and organising the design and the construction, and once it's built, it'll be handed over to the Greek state to run and maintain. As has been said, I led the exhibition team developing the structural engineering design, but doing something like this, it really is a whole team effort. So it takes a huge amount of courage on the part of the client to go for it and build something like this. There's Renzo Piano and their local partner architect Bettaplan, and it's really their vision and their conviction that makes it happen. There's the project manager, Faithful and Gould, and they've been very supportive, making things happen. When we say we want a test to happen, it happened. So it would never have happened without that either. We'd never have got it through being able to demonstrate to other people it would work. Arup have done the services engineering with LDK, their local partner, and obviously it's all about services, creating something to support the canopy, the photovoltaics. And then we've got our local partner consultant, Omite, and again, getting it through the Greek approvals process. We wouldn't have done that without their support. And then finally, we've got the contractor, which is a joint venture between an Italian company, Infragilo, and the Greek company, Yek Turner. And they've really engaged with it, taken it on board, and are really making it happen. I've been very impressed going around their production lines and their facilities. So those are the key big players, and there's certain other key players who I'll mention as I go through it, as long as I remember the right points. So it's in Athens. The blue ring shows the centre of Athens, where the Acropolis is, where the historic centre is, and the red blob is our site. And that's the Renzo Piano image of the canopy at sunset. All the nice renderings in the talk about pianos, and the scroffier sketches are by us. But what this nice rendering does show is the canopy is way up there above the Opera House and above the park, and it's also up above nearly all other buildings in Athens. So it's going to be something which you can see from pretty much anywhere in Athens, and it's really going to be the marker for our project for this site. So why on earth did we choose to do it in ferro cement? Surely if you're going to do something so visual, something that everybody's going to see, it's got to be there for a long time, you're going to choose to use tried and tested methods. Well, we didn't initially plan to do it in ferro cement. We developed a scheme with a steel tensegrity structure canopy. We went a long way with that scheme. The idea was it was going to be a little mist floating above the buildings with some photovoltaic leaves up there. And as I say, we went through that all the way through scheme design, detail design, and then as we got to the end of detail design, there's all these other bits added in. You've got all the secondary support systems for the photovoltaics, you've got lots of access maintenance walkways, you've got cables, a phenomenal number of cables for photovoltaics, inverters, transformers, and it really doesn't look much like a mist anymore, perhaps a bit more like a thundercloud. And there was also just this thing, the canopy's up there above the Opera House, and it's a thing which is obviously there. It's an ideal place for the marker for our project. And yet we had this supposedly transparent mist up there, and was that really the right thing to be doing? Surely we should be making something which is going to be a marker, not what's going to disappear into the Senian haze. So Renzo called a little discussion session down in their general office. They've got a lovely general office, and we had a very enjoyable but incredibly intense afternoon in his samples library. And very quickly, we came up with the criteria which we actually had to meet. So we had to have simple supports for photovoltaics, easy maintenance access. We had to have somewhere to put the transformers, the inverters, the cables. And as Renzo was very sure now that if we were going to create this umbrella over the site, it had to work as an umbrella. There's no point letting the rain fall through like we were letting the wind blow through it. We had to collect it. And then the bottom surface, when you're standing on top of the opera house, which is going to be accessible to everybody, you're only about 10 meters away from the bottom of the canopy. So it really had to look good. And it had to be smooth, low maintenance, and free from joints. That came up again and again in the conversation. No joints in that finish. So the other parts of the brief were, in that conversation that afternoon, was it had to have a finish like a yacht, the hull of a yacht. This happens to be a ferrocement yacht, but when we had that conversation, it was just to finish like a yacht. This is St Giles, just around the corner from here. And what came up in the conversation was we wanted durability, something like ceramic. These are ceramic cladding panels, but without any of the joints. It had to have a thin profile. That's, again, really, really important, but it had to be something definite, not something that just disappeared into the haze. Structurally, we had something that was curved in two directions that adds interest for trying to get your finishes looking good. And this was a big one. We had to be able to get competitive tenders. It worked. And then the other bit was, we're now at the end of detailed design, just going to start producing all the construction information. We're changing everything goes up here. There's suddenly going to get a lot more windows on it. It's going to have cladding apparently. And it all sits on top of the opera house. There's well over 100 people working away on the opera house doing reinforcement details, shuttering patterns, door schedules, where all the ducts are going to go, sprinklers, etc., etc. We couldn't do anything up here, which meant that they had to revisit that work. There's no scope to extend the program or to redo their work. So that was an intense afternoon. The obvious thing to do is something tried and tested. Obviously a steel frame with some waterproofing on top of it and cladding below it, something visual. That didn't work for us structurally because once you had all those layers, you've got a structural frame, waterproofing on top of it, cladding below, it all got too heavy, we couldn't support it in the opera house. It didn't work architecturally because once you got all those layers, it just got too thick. It wasn't what Renzo wanted. And also on the bottom surface, if you've got a cladding system, it's really hard to avoid having some joints which you see. So it wasn't going to be that. So it looked like it was going to be some kind of a monocoque structure, which to me means that the skin is going to define the form. It's also going to take the structural loads. And we ran through every possible option. I think, well, I'm sure we missed something, but we talked about steel. We had concerns about the durability of that with the paint finish. We talked about stainless steel. That wasn't going to do it with the costs and also the weight. We talked about aluminium. That didn't do it with a jointing system because either riveted together or connected mechanically in some way, which was too visible, or you weld it, in which case you actually lose a lot of the structural performance. We talked about plywood, but nobody believed that was going to be there in 100 years' time. We talked about post-tension concrete, and we ended up with ferrocement. There we go. So we've got the two ferrocement skins, top and bottom, separated by steel bracing internally. And there's not really anything particularly special about that. It's no more, in a way, it's no more than a steel girder, and we just happen to replace the top and bottom chords of the steel with very thin concrete with ferrocement. So it's a composite structure, but composite structures have been built before. And just what I'm taking to mean by ferrocement here, in a brief comparison with ferrocement with standard concrete. Ferrocement on the left, standard concrete on the right. Ferrocement is thin. This is a sample cut from one of our panels, test panels. It's typically 15 up to really upper end 60 mil thick maybe. Standard concrete would start at 150 mil. The cover is a thing that really throws all engineers when we get involved with the first time up. Standard concrete, you're really talking about cover from 25 mil or more. Ferrocement, it's 3 millimeters. And the cover is what gives normal concrete, or gives concrete its life. It protects the reinforcement from corrosion, from the water, from the air. So, how on earth is that going to, no, there's no way it's going to last. Reinforcement bar size is obviously smaller than ferrous cement. But this next one about the reinforcement percentage I think is interesting, because actually in standard concrete you might have 3% reinforcement in the direction in which it's working, carrying the load. In ferrous cement you typically have something like, say, 3% reinforcement in each direction. So it's not that different in terms of the reinforcement amount. But what is hugely different is this bottom one, which is way out there, something we don't normally talk about, which is the surface area ratio. And what that is, it's a ratio between the surface area of the steel, the total area of the steel bars in there, divided by the volume of the concrete. And as you can see here with ferrous cement, it's something like 20 times higher than it is with normal concrete. And that is what I think really helps to contribute to controlling the cracking. So that's a key thing. This is one of the standard sections we use on the project. It shows a 20 millimeter thick section, 3 millimeters top and bottom of cover, and then a lot of layers of steel mesh all tied together, all right up against one another. These words, I really like this phrase. For me, it is what ferrous cement is. And I think I got it off Patrick, I'll introduce shortly. Ferrous cement construction uses standard construction materials and techniques, which is really important for us if we're going to tender it, to form unusually thin reinforced concrete. Right, so we're going to do it in ferrous cement. We've had a really nice, sensible program for developing the design. Started in Easter 2008, went through feasibility stage, a good year of scheme design, nearly a year of detailed design, and we're now into a few months into developing the construction documents to go out to tender in the summer of 2011. And then on the 22nd of October 2010, we decided we're going to do this canopy in ferrous cement. We've got some work to do there. So the first step was to convince ourselves we could actually do it. That's the whole team convincing ourselves. Architecturally is easy. Renzo had worked with Michael here previously to do some ferrous cement elements at the Domino Museum in Texas. As Michael said, Renzo's also built his own ferrous cement yacht. Pianos know that they're going to be able to create the geometry and the finish they want. So I just left the poor structural engineer to work out, convince ourselves that we could make it stand up and last. Doing our precedent search, it was a bit mixed really. There were ferrous cement examples. There's obviously the work by Nervi, his yacht, his Turin exhibition halls. There's an example in the Schlumberger building in Cambridge where ferrous cement's been used for permanent formwork. And then you've got another barge there, a water tank. Obviously it can be waterproof. The image at the bottom left is in Cuba, and it shows, I put that in there because it illustrates how ferrous cement is largely used as more of an arts and crafts type thing. But nonetheless, those have been there a long time in Cuba, and they've weathered very well apparently. I haven't seen them. And there's a few projects like this one up in Indonesia. They're on a smaller scale than us, but they do show ferrous cement in buildings. So precedents weren't that great. They were there. And then what about design guidance? Well, we convinced ourselves, and Eurocode 2 does make provision for design of thin shell concrete. It just says you've got to account for everything you don't normally think about. All the second order effects, how it deflects, etc., etc. So hopefully we can argue that it falls into Eurocode 2. And then these are the other codes. There's the ACI guidance, which Michael and Paul both mentioned, and Professor Nauman's book. They were both absolutely key to us. Fantastic references and various papers about durability of ferrous cement. They didn't go into as much detail as we would have liked for helping us design our thin shell with its curvature, long-term axial loads and stuff. But they did confirm, which is critical, that we could use standard reinforced concrete theory. And that was the key to really giving us the confidence that we could analyse it. And then these two gentlemen were critical for us. Patrick Jennings is a structural engineer for, I think, all of the more recent large ferrous cement structures. And Paul Nedwell from the University of Manchester, who we've heard from. Paul organised a fantastic hands-on workshop day for us in Manchester, where we found out what ferrous cement is, tying all these little layers of mesh together, and found out actually there's an awful lot of tying, a lot of work. And we also found out about trying to get the mortar to penetrate through the mesh. It's hard work. Trying to force that mortar through, and as you can see in the bottom right there, we weren't that successful. But what we did get was the confidence that actually with a bit of practice, skilled labourers not like us were going to be able to do it. Paul's talked about the bowl footbridge. This was an important example for us, hands-on, an experience to really sense the material. And this little sample, Paul's talked far better than me about what that shows about how, even when you have got bits of steel exposed, actually it doesn't cause the spoiling to continue further and further. So that was very useful. And then Paul has also talked about these, but they were critical to us. This is roof samples. 20 years in the roof of Manchester, and they still look pretty good. Well, very good, actually. So that was all very reassuring. And then Patrick, these are 3 of Patrick's projects, a mausoleum in Jordan and 2 headquarters projects in Saudi Arabia. When we spoke to Patrick about the way that they'd worked, the way that they'd tied the ferries to the mesh together, how they'd actually managed to reduce the labour requirements, getting the mortar into it, that gave us a confidence, actually, yes, we can build it. So we're convinced. We spent 2 months, end of December. We've got another 7 months to tender, and we've got quite a lot to do. Next step is getting a design. So this I've talked about. It's 2 skins of ferrous cement separated by steel bracing. The ferrous cement skins are thin, and they're taking big axle loads, so we had to put ribs on them to stop them from buckling. And that's a concept on the right, and one of the sample panels on the left being the other way around. On your left, there's this concept being lifted into place on the right. And what the ferrous cement skin allowed us to do at the edge of the canopy was it allowed us to take that structural skin and just sculpt it round to create the gutter. Ferrous cement is waterproof. We didn't need then to have a separate lining. That was it. We tied everything together. And then the water was taken from there in pipes into the canopy and then down inside the columns. The form finding, the principles of the form finding in this project were, again, pretty straightforward. We had the edge of the canopy had to be very thin. The red arrow above the first column was us. We needed that to be a certain minimum thickness so that it would stand up, not snap off, and not wobble too much. The guy standing at the bottom represents what it was going to be like to experience it underneath the canopy. And that really defined the bottom surface. So then it's really left with defining the top surface, which we wanted that to be as high as possible, because the further apart the 2 skins were, the thinner we could make them, the lighter it would be. Renzo wanted them to be as close together as possible because it looked thinner. So there's a bit of toing and froing on that. And the final point really feeding into it is about water, rainwater. We needed to make sure that we kept enough of a fall on the top surface so that even when it deflected under snow and ice loads, which it does snow in Athens, the water wasn't going to pond, it would still drain off. So we created ourselves, we wanted to create something where a standard kit of parts really. So we chose 5 meshes, 5 standard meshes for us, with wires from 0.8 millimeters to 10 mil, and a grid of 6 mil to 50 mil. And then we use those 5 meshes to create 5 standard thicknesses. We went from 15 mil up to 55. That's since been rationalised a bit. There's no 15 mil stuff in there now. And what we did was we then just took our analysis results, found the areas which are working hardest, put the thickest ferrous cement in there. The areas which are working less hard were thin. That was it, really. Simple. That's the design. There's a bit more to it. This is a section through the canopy. We've got the 2 skins again, ribbed ferrous cement skins top and bottom, and then with the steel bracing internally. Basically, the design team got ourselves in a bit of a knot about how we're going to support the PV units, and ended up with upstand ribs to do it. I'm glad to say the contractors changed that detail, so all the ribs are downstand inside the canopy, which makes it much cleaner for rainwater runoff. And then the other key thing really is how the bracing connects to the ferrous cement skin. What you'd normally do, if you've got steel beams in the concrete core, say, you'd cast some steel plates in, weld a thin plate on, and bolt your steelwork to it. There's no way we're going to be able to do that. If we had concrete that was thick enough to cast steel plates in, it all got too heavy. So we ended up with something like this. We do have big loads which you have to transfer between the steel bracing and the ferrous cement skin. And we developed this spider detail. So steelwork comes in, you've got these steel spider brackets, and then we've got a little thickening in the ferrous cement to create this plinth, and all the loads are transferred, all the horizontal loads, the shear loads, which are transferred in bearing of the steel plates onto the ferrous cement plinth. The little bolts and things that you can see are about locating the steel bracket in relation to the plinth, not about transferring the load. So we also had, I'd say, big loads, we had to make sure the plinth didn't slide across the ferrous cement skin too. With normal concrete, where you've got a big horizontal shear load, you put shear links in, they're 12 mil, whatever, diameter. And the theory said we could use standard reinforced concrete theory, so we did. We put in hundreds of 1.6 mil diameter shear links, like so. And what's interesting is when we did the tests, it really does work. It's, you can apply that theory, the standard theory. And yeah, there's a lot of labour. There's also a lot of connections. There are 2,000 different connections, all different bracing angles and whatnot. And Tion in our office did a fantastic job coming up with a way of rationalising them, scheduling it all and communicating it to the contractor. We had a similar issue with the ribs and the connection between the ribs and the skin. We needed to make sure the rib didn't just slide along the ferrous cement skin. So on this diagram, either side, you've got two dark lines coming through here, which are shear links. And again, it's these diddly little 1.6 millimetre diameter wires, shear links. Again, a lot of labour, but they do work. Durability, Paul's talked about this. Lots of fine meshes. We've got a high strength mortar. We've got 3 mil cover on each side, and it's important that we actually achieve that cover. If we get too little, obviously it doesn't protect the steel. If we get too much cover, well, it makes the canopy too heavy for one thing, but the other thing is that too much cover gets the mortar away from the reinforcement, which is stopping it from cracking, and you might get cracks starting. So lots of cover, lots of spacers, 3 millimetre spacers, quite diddly. And then the silica fume, which Paul's talked about, that fills all the little micropores in the, well, to understand that fills the little micropores in the cement matrix and stops the water, the carbon dioxide getting in. But it really does, well, as Paul said, that silica fume is key to making a difference. So we had something that was waterproof, should last, according to all the theory, and that should be it really. But what we did do, we decided for belt and braces, we put a layer of epoxy paint over the top of it, which could be touched up from time to time. It didn't really matter if they don't touch it up, but it adds waterproofing in the chloride barrier. So that was it in principle. That's a whiz through the design for the canopy. That's the shape. There's a couple on the top surface. There's a slot to get air in and out to ventilate the inverters, transformers, and also get people in and out. That's got a steel picture frame around it with some struts across. And there's a mast, a little mast to be supported off it. So we've got a design. We've also got to build it. There's lots and lots of ways of building ferrous cement. You can just create your armature, your mesh, and then apply your mortar onto that. You don't get particularly accurate geometry, but you can do it like that. You can create a one-sided mould, lay your mesh onto it, and then push your mortar in to that mesh. You can put your mould in the middle and put your mesh both sides of it and mortar it. And then you can apply the mortar by hand, trialling it on. You can spray it on. Or this is showing something that Patrick had developed previously, injecting the mortar into the mesh. So it comes from the pump, and then you've got various nozzle heads, and you use the pressure from the pump to force the mortar through the mesh. We needed to have a good quality bottom surface for visual reasons, but also structurally. If it was way out of tolerance, it wasn't going to work structurally. So we chose to have a single-sided form, lay the mesh onto the form, and then to try and reduce the labour requirements, we chose to inject the mortar into it. So we've got a design, we know how we want to build the little bits of ferrous cement. We've also got to get it up there above the Opera House. We were very keen as engineers to do it in situ. All joints together nicely, no risks. So, but to reduce the amount of formwork, scaffolding, the volume, there's just loads and loads of meters cubed of scaffolding. So we're going to build at a fairly low level above the Opera House and then jack it up above the canopy, above the Opera House rather, using strand jacks. That was great, fantastic structural engineering design. And a little taxi ride I had with Neil Clemston of Faithful and Gould, about a minute to convince me it was wrong. is going to add months to the construction programme and loads and loads of money. So by the end of the taxi ride, we had a pre-casting system where we're fabricating lots of small units, lifting them up into place, and then making in-situ splices between them. We've got a design, we've got to prove that it works, and we've proved that it can be built, and we've also got to persuade somebody to build it still. The proof one on the analysis side is some independent analyses. Obviously, we had a massive task doing our analysis. Omite, our partner consultant, our local sub-consultant, did a similar independent analysis, which came up with similar results, which is reassuring. We also commissioned a company called ANSYS to do some local finite element analyses, very detailed ones, to check that actually the results it gave on when the ferrous cement broke was consistent with a little piece of software we'd written, which it was, thankfully. Next step was doing some initial samples, and what we did there was we appointed a very small local contractor and took local labour who had no experience of ferrous cement and proved we could make it, basically. So this is one of the first bits, tying some bits of mesh together, and you can see the little grey dots there. They're the spacers, 3mm spacers, to make sure we got the cover we wanted. Console team set up this very effective production line to create, at the top right, you've got the spacers. A little epoxy thing cast round is a wire tie. It worked really well. And low-key, but effective production line. Prefabricating mesh reinforcement, the main bars for the ribs, wrapping them in a fine mesh, and then lifting them on and tying them to the mesh for the skin, and then getting the mortar on. Injecting the mortar through. Console team's labourers were a lot more successful than us quite very quickly. This is one of the early attempts where there's too much mortar, but it does work. These are two examples of the heads. There's a bit of trial and error in developing heads, cutting bits off here and there to get them to do what we wanted, but they did that. And fairly soon we were getting samples which looked okay on the top surface. There was then an exercise of just what sort of finish do we want on that top surface, and so there was a lot of different samples, lots of different trials. We tried different types of trowel, metal trowels, wooden trowels, sponging it, and ended up agreeing a particular type of finish. I can't remember which one it was. Similarly, on the bottom surface, there was a similar exercise to find out how we're going to get the finish we wanted. This is one of the early trials. You can see the crack across it shows that actually we still weren't getting great penetration through beneath the ribs, which are on the other side. But this was cast on a Perspex form, and the finish is just too good. We can't get paint to stick to it. So we tried a few things, but actually wood, timber was what we decided to run with. And wood gave us two things. It gave us an acceptable finish, but it also meant that what we could do is once we'd laid the mesh onto it, we were very worried about when we injected the mortar in through the mesh, it was going to lift the mesh off. So if we got a wood form, we actually could put steel staples through the mesh to hold it down onto the formwork. That's one of the early examples there. Again, still having trouble getting that penetration through under the rib, but they did fairly soon get there. You can see a few of the staples sticking through if you look closely on that one. We were going to need some way to create a curvature, and every panel was going to have a different curvature. So we came up with a system where we'd have a load of threaded studs. You can adjust the threads, and that would change the geometry of the formwork, so you could then get it right for the next panel to be placed. And that was it. We knew we could build the panels now. So we started producing panels and the initial tests. There's a short video which we'll hopefully play next, and it shows Pete, the first person in it is Pete Winslow, who's a project engineer for the project, and he's in Athens tonight doing something to do with the canopy. Okay, we did struggle with health and safety throughout this stage, but Nobody got, throughout the sample panels and building a prototype, I don't think we injured anyone seriously. But we did, with a small Greek contractor, there was a struggle. No hard hats. This is that hammer drop test. Everyone was very worried about a 15mm thick panel. It's going to be brittle, blah, blah, blah. Actually, where he's pointing is where the hammer hit. The two marks on the right-hand side are actually where there's some holes through the ribs for lifting it. So it performed very well. And I think those 3 tests, people jumping on it, this is 15mm thick ferrous cement, people jumping on it and throwing the hammer up, they were possibly the most important tests we did. Nothing scientific about them, but it was all about us getting a gut feel that it did work. But also that video of Pete jumping up and down on it, that's been shown any number of times to everybody to give them an idea what this material is. Another chance to see Pete looking silly. Right, we've done our initial tests. We're at the end of March, and we still need to do a load of formal tests to show that actually the ferrous cement does break when we say it'll break, and it carries the loads we say it's going to carry. It's getting pretty close to our tender date, but we're pushing on. So the formal tests. We built 48 2.5 metre square panels, which we broke, or tried to break, and a few smaller panels. This was all done at the National Technical University of Athens, who I must say they were also fantastic, and just engaging with it, making it happen, working over Easter weekend and things. The smaller samples we could break using their existing jacks and things, but we had to build our own rig to load test the panels, so the rig allowed us to apply a load in 2 different directions, so we could see how they interacted. One of the early samples, the one direction loading there, and most of the tests we had a camera crew down there one day to try and get some exciting photos, and nothing happened. So you've got somebody bent over reading how the microgauge is changing. This one was an interesting result. It's what shows what happens if you don't have the shear links in between the rib and the skin. So the shear links do actually do something. Shame that we had to put them in. So the formal tests were completed around the end of June, which was just a month away from the tender date. So we did get a pack out for tender, but finishing off the analysis of the test results and everything pushed us through some more months, but it did work with the tender process. And Chris Mills from our office had a fantastic summer analysing it all, showing how the test results correlated with analysis. So we've now got test results. We know it's strong enough, we've demonstrated it's strong enough, but we were very keen. Ever since about January, we've been saying we want to build a prototype building. We need to build a prototype building to demonstrate to the contractors that actually they can build it. And we wanted to build a section from the canopy. So we chose a section 6 metres by 16 metres near the corner where the curvature's fairly great. And there's our design, 16 metres by 6 and about 5 metres high altogether. That includes the little stub columns at the base. The first thing that everyone was very nervous about if we're going to build this prototype is the connections between the steelwork and the ferrous cement. That is just a maze of shear links, tiny little bars, bigger bars. There's no way we're going to get mortar penetration through all that, are we? So we assembled one, applied the mortar, left it to cure, got a bit nervous, and actually it worked fine. So that was very reassuring to see that Constantine's team by now were good. They could get that mortar penetration to work. It wasn't what we wanted to do is to demonstrate the system we're proposing for the main canopy. So we didn't build the prototype in the cheapest way, because we wanted to have our adjustable screws and threads. So you've got a steel frame, put your adjustable formwork onto it. Really important to get a good finish, no joints no steps between different bits of formwork. And then prefabricate, or pre-assemble, I should say, the mesh, lift it onto the formwork, mix the mortar and pump it in. None of it, none of this was a laboratory exercise. It was all low-key, low-tech, but with a lot of focus on detail, really. Yep, health and safety wasn't what we'd like, but nobody got seriously hurt. And I'll say the main contractor who's building it now is an awful lot better, health and safety. This was getting the mortar on there, and the little sample is checking the cover. In practice, once the plasterers had their experience, their hand in, they pretty much hit the cover. And this was just proving by dipping that actually we were getting a 3mm cover to the top surface. Another low-tech solution that really worked, a pour stop at the end of one day. Take the nails out and you can continue the next day. There were still a lot of people. One of the things I'd been keen on was to try and reduce the labour requirement. But we still had a lot more people than I'd really wanted, a lot more labour. But it worked. This is the bottom surface finished. And very early on, we took some of the formwork away to check we're getting penetration in the more difficult places. So you can see the steel staple sticking through. And in the top right corner there, you can see some cracks, which we took the formwork away before it finished curing. And like any concrete, ferrous cement needs to cure properly. Otherwise you get shrinkage cracks. And this is really about prototyping the prototype and prototyping bits of it. It just meant before we incorporated anything into it, Patrick made sure that everything was, we knew we were going to be able to do it and get it right. So this is a little section of the gutter, some of the diaphragms. So it's proving it can work before you incorporate it. And there's a finished prototype. It came up nicely. It still looks a bit chunky, and that's because of the sections that we used in the prototype. They were easy to connect. In the main canopy, they don't look quite so chunky. We did a little load test. This is just the serviceability loads on the cantilever to see how it responded, which was, there's a little bit of slippage of bolts and their holes, but otherwise it was pretty much spot on our calcs. And then we left it for 2 years. This is a couple of weeks ago where we tried to break it. And the big bags are 1-ton bags, and small bags are 80 kilograms, I think. And that we ended up with 110 tons in it, which is twice the ultimate limit state load. So any architects, engineers always over-design everything. We ended up, as I say, we loaded up more than we thought we were going to be able to, and we ended up scavenging Kentledge and precast bits of concrete from around the site to try and break it, but it was getting unsafe. We did actually pay attention to health and safety. The concrete blocks stacking up that high weren't going to be safe when it collapsed, so we stopped and failed to break it. On the plane back from Athens, Pete and I were flicking through the in-flight brochure and realised the plane with the Airbus we were on coming back from Athens, fully laden with people, cargo and fuel, at takeoff weighed 89 tons, and we had 110 tons on the prototype. Which, something like that, that's what makes you understand what you've really done. This is a graph for the engineers, and it's really exciting. Because what this is a plot, it is actually, it's a plot of the deflection against the applied load. So the vertical axis is the tons applied to the cantilever bit, and the horizontal axis is the deflections. And the key messages from it are, it starts off with a nice straight deflection, which then the rate of deflection increases as the load increases, and then when you take the load off, it recovers more or less the initial rate of deflection, which we really weren't expecting. We expected it to just deflect at a more or less, just deflect a more or less constant rate and then fail suddenly, either with the buckling of one of the steel elements or buckling of the concrete or something pulling out the ferrous cement. So this was a very reassuring thing. I'm not sure exactly why we've got that load, that ductile shape, but we haven't relied on it. The whole canopy is designed assuming a brittle material. I mean, this shape could be because of deformation of the steel plates which the bolts go into. It could be because of cracking the ferrous cement. There could be loads of reasons, but I don't know. So that's the prototype happened during the tender process, really. But it did happen in time. It was complete about halfway through the tender process. The key reason for the prototype was to persuade somebody to build it, persuade them it was buildable, and so people couldn't come back and say, you designed something unbuildable. During the tender period, the mid-tender interviews, or more like the first quarter interviews, we had all the contractors on site. We'd had them down there, walked them around it, touching it, seeing what we're doing. And once the prototype was finished, they all had the opportunity to come to site again and see that it could be done. Very welcome to talk to us. It's open. We wanted them to understand how to make it happen. And it worked. We got the tender documents allowed the contractors to submit an alternative proposal. And we did get 2 alternatives back, but they didn't satisfy the design criteria. And we also got, I'm pleased to say, some compliant tenders back, so we're building a ferrous cement canopy. It's a relief when the tenders came back and gone through that process. This is Opera House. The Opera House is nearing topping out, so they'll be building the roof slab over the Opera House in the next few months. And then the canopy panels should be started to being lifted in, I guess, sometime in the autumn. Impregido Turner have done a lot of samples, proving they're going to be able to do the more complicated bits and get an acceptable finish. This is one of the corners, the sample in the corner. That's going to look okay once, and that's the corner from below. This is a splice where 4 precast units have been spliced together. It's come up very well. All we need them to do is to repeat that across the canopy now. They've got a very impressive production line set up. They've got four lines to create, I think it's 710 precast units they're producing. And it's nice to see a lot of the details we developed with Console team and Patrick during the trial period and the prototype being followed through. So this is the adjustable formwork system. They're actually using a steel form rather than a timber form that we had, but we've got the same principles for adjustment. You've still got a lot of labour tying it together. We've not got rid of that yet. There's a mammoth exercise in quality control, and when the panels get up there, they've got to fit together. And each panel is like a hospital bed. It's got its documents that travel with it everywhere, telling you exactly who's done what to it and when. To hold the mesh down onto the forms, if they've got a steel form, they can't staple down to it, but they've got this cutting system of girders, which have then got these threaded studs which push the mesh down against the formwork. It's very effective. Impregido have developed a way of getting the mortar into the mesh, so rather than using the injection method, they're casting each panel in 2 pours. First of all, they use a very high flow mortar to get the mortar into the bottom skin. They then insert a mould in between the ribs, and then they can use a high flow mortar to get the mortar in around the ribs as well. So that takes a lot of the labour out of getting the mortar into the mesh. And this is a finished panel. Again, it's a development of what we've got, the same principles, but rather than placing the mortar with the steelwork spiders in place, they've got some location studs and some sockets which locate the spiders in place. But it's still a bearing of steel plates onto the ferrous cement to deliver the loads. This is a precast unit off to the storage yard. And once they're in the yard, they're all wrapped to control corrosion of the fine meshes and kept in place until we're ready for them. So, a couple of thoughts on innovation and on a few thoughts on ferrous cement. The innovation is hard work. And what you come up with is, it's just there are no standard solutions. You just forget how often you use a standard steelwork connection, a standard reinforcement detail. And when you're doing something like this and you're trying to work out how to get your 1.6mm damaged shear links in, it's totally new. There's an awful lot of work goes into developing those details. And finally, it really relies on engagement by the whole team. And we've really had that on this project. It's been fantastic. And by engagement, that's not just mad enthusiasm is going to work. It's asking the right questions at the right time. So we have had difficult questions from the project manager, from the client, but they've stuck with it, and it's being built. And on ferrous cement, it can go both ways. It's obviously still suitable for an arts and crafts product, but I think we've demonstrated that it can be a well-engineered product. There is scope for improvement. Paul, I'd like the design guidance to be more helpful on designing your thin shells to take account of all the secondary effects, how it's going to creep under long-term loads and then respond to short-term storm and earthquake loads and stuff. And the production line, I think, can be improved and get rid of that labour. And next one is my little fantasy production line, where you've got the production line going from left to right, your mould coming along first, your form coming along first, using some kind of a post-it glue to stick your spaces on, unravelling your mesh on, some nice little electromagnets to hold the mesh down onto the formwork, a bit of nice high-flow mortar which will just flow around the mesh. Once it's cured, you turn the magnets off, you no longer need the ties, and you can just cut it to length. Very simple. Honest. Just somebody needs to do it. The next bit is how you connect the ribs to the skin, where we had this system with lots of tiny little shear ties, shear links, which is a lot of labour. I think there's probably a version there with the carbon fibre or Kevlar thread. You keep it taut while you place the mortar, and then once the mortar's cured, it's okay. But that was a step of innovation too far. We didn't want to be trying to do more. So there might be something there. Or I think there's also a version now where you can probably just epoxy the thin ferrocement skin onto steel joists to create a composite structure. One note, if you're going to be using ferrocement in floors, is it is thin and light, so you need to be really careful about your dynamics and also fire protection. It's not like normal concrete. It hasn't got the same cover, and it will fail more quickly in the fire. So I think it needs fire protection the same way as steelwork does. Probably a bit less, but basically the same. Michael strongly disagrees with me, I see. Good. And as Michael mentioned earlier, there's options for doing it as permanent formwork for concrete. It's obviously a nice, ideally thin product which you can use as like this twin wall product here. And there might be ways where you can join your twin wall forms using the kind of splicing detail that we're using on Athens, which would give you a uniform, nice finish. So this is what we hope to see sometime late next year. And that's it, guys.